Welcome back to the part C of lecture 4. This part we are going to discuss the hands-on. We are going to do some hands-on of fitting linear models with feature engineering, etc. So for this, we are going to use the weather data of Indian cities from the Kaggle. I'm going to share this data, this website, this thing, this page with you guys, as well as if you I'm going to share the data. So we are going to use the data for Chennai. You can try the same thing with other cities as well. So here is all the data sets are available. So we are going to use the Chennai data set. The data set is available from 1990 to 2022. Okay. So what we will do, we will first start our studio. Okay, and in the R studio, first thing we will open is our script and an R markdown file. R markdown file. In the R markdown file, we will first write that hands-on for lecture 4. We will choose PDF. We don't need. Okay, and then what we will do, we will just save them as a hands-on for lecture 4. And the first thing we have to do is we have to read the data. So data equal to read.csv file equal to Chennai 1990 to 2022 madras.csv header equals to true. So here is the data that we have seen. So this is the first day of the data. So if you look into the date, it is like day first, then month, then year. And if you look into the structure of the data, it is the structure of the data is it is a data frame with 11,894 observation and 5 variables, and time is stored as character. So we have to do it properly as a date file, as a date column. We have to store it as a date column. Data $time format should be percentage date first, then percentage m, then percentage year. Now if I do that and if we just check, it is read as this way. And if we now structure of data is like this. Now you can see the time is read as date with format in this format. So now it is a date format, not character format. So the first thing we will see is we will split the data into train and test. Split the data into train and test. So data train equals to subset data time is less than equal to as date. Now we have to give it in this format. So date, month and day, year, month and day. So the first thing will be 2015, then month will be 12 and day will be 31. I hope this is fine. And then let us try. So now in the train dataset you can see 9,496 observations are there. So it's starting from 1990 and last day is 31st December 2012. So also if I just say tail of the data train, so up to the last day is 31st December 2015. 31st December 2015. This is the train data. So same way we can define the test data. So we will just take the same thing. Instead of less than equal to, we will make it strictly greater than. If we do that, test data has 2398 and the first day is 1st January 2016 is the first day of the data, and the last day of the data is 25th July 2022. So this is what we are going to do. Now what we will do, we will put it in the neat R. So first thing is we will keep going, read the data. So up to this we can just put it in the data part. So here, and then if we just run it, so here in the R markdown nicely it is come in a PDF. You can create the report of your analysis alongside whatever you are doing. So this is very important. When you are doing analysis, you create the report as well, whatever you are doing. So this is a very handy thing in R. So read the data and then split the data into train and test. R so okay, we can just write it in this way, and data test. So here is the splitting the data. We have train data we have defined, and here is the test data. Now what we will do, we will do some visualization. Let us go there, and in the main R script, let us do some visualization. Okay, in the visualization what we will do, we will take the from the train data, we will take the time on the x-axis and data train as the average time. We will plot them. So you can see, so this is how it looks like, somewhat sinusoidal. So what we will do, we will put a PCH equal to 20. Alright, yeah, it looks like somewhat sinusoidal. Every annual behavior is sort of there. So in order to just make sure if it is truly that, we can do is 2 into maybe 3 years of data. We can plot 3 into 365. Yeah, so this is from 1991 is one cycle, 91 to 92 is another cycle, and 92 to 93 is another. 3 cycles, 3 years of data, and it's a sinusoidal behavior as expected. Now what we have is, if you look into the plot, the Y lab is bit cryptic and X lab is also bit cryptic. what we can do, we can, in XLab we don't need to give anything, it is some sort of self-explanatory. In the Y lab, in the Y label, the label of Y needs to be given. We say average temperature. Okay, so this is average temperature. So we will try to fit some kind of sinusoidal model in the for the average temperature. So we can put it in R, and in R markdown we have to just say R, and here you have to say fig equal to true, so that it will produce the figure as you wish. So now you can see it produces the figure as expected. If you don't give this figure equal to true, then it will not produce the figure. Okay, next we want to fit a model. So what model we want to fit? Let us first fit a model. Fit model. First model that we want to fit is some kind of sinusoidal. So we can use in R markdown the average equals to beta naught plus beta 1 equal to time. Now that will create, if there is any trend is there, and then beta 2 times sine maybe omega t plus beta 3 times cos omega t plus some error. Okay, this is the model that we want to fit, but we have to, at the same time, we have to say something about the omega. So omega, where omega is equal to 2 fraction of 2 pi of p. Now this p is 365. This p is our daily data is 365. Okay, so this is the model that we want to fit. Okay, so this is the model we want to fit. So first thing we have to do is we have to first thing is omega equal to 2 pi by 365. Pi itself is defined as 3.141, so omega will be like this. Now we have to have, if I go there, I have to have a time to be defined. So what I will do is here, and this time component we will require both in train and test dataset. So what I'm going to do is here, before the training and test, I'm going to TMS a new variable which is quantity to n, where n is n row of data. Now the problem will be, if you take a look into the data TMS, it is starting from 1 and it is going into 11,894. So it is better if we just center the time. It will just handling the data will be better. The coefficient will be a little bit meaningful. So what we will do, we'll just subtract the mean of these guys. Okay. So if I do that, then it is starting from minus 5946.5 and it is going ending at 5946.5. So it is just shifting the horizon, shifting the time from centering at 0. Now if I just run the whole thing, it will be no problem. So we have to add this part in the markdown file in the beginning. And now if I just run it, you can see the TMS has taken care of. All right. Next, what we will do, we will fit the model. First model. One emoji. TMS omega times. We have to provide data equal to data train. And if we just put summary, now this is the first model to fit. Now what are the, let us spend some time to understand what is going on here. The first is the intercept of the model, that is beta naught, and then second one is this is the coefficient corresponding to t. So if we look into the markdown file, so beta naught plus beta 1 t. So this beta naught, beta 1 times t this is the standard error, this is the t value, and the p value is really small. So that means with increasing time, the average temperature in Chennai is increasing. This is sine omega t, which has a significant effect. This is cos omega t. This is the coefficient of the, say, beta 3. This is beta 2, and this is beta 3, and both of them are significant. Of course, sine, cosine will have a significant effect, but the most important thing is trend is significant and it is positive. It's very small point after 50421, so it is increasing at a very slow rate, but we cannot ignore it. It is small enough, it is significant enough, and it is saying that it is increasing over time. Now what we are going to do is we are going to plot the model. We have to see just how the fitting is working or not. So before plot, what we will do, we will in the data train, what we will do, we will just take the fitted values equal to NA. We are creating a new column with all NAs, and then data train, row names, and then mod model So we have taken from the model, we have taken the fitted values and we put it in the train data set. We extracted those values, and so now we can plot the train $time data $t average PCH equal to 20, color equal to gray, X label is, we can keep it empty, while equal to average temperature. First we are taking these, well, we can take the first few years to just understand what is going on. First 3 years, and then lines, we can just take this comma, but instead of T average I want fitted values. First color equal to semi-red, line width equal to 2. Now I just I have not closed this gap. Yeah. So now if I just zoom it, you can see that the fitted model is doing very nicely between going through the sinusoidal way, going through the middle of the points. It's not doing pretty bad, but there are quite a few are from far away, quite a few from bit down. So this is maybe June, July, where a lot of rain happens. So that time, during the rain, the temperature drops. So average temperature drops around that time. Now what we can do, we can take from the summary. If you look into the summary, this residual standard error is 1.38, which is actually the sigma. So we can take the sigma and summary, we can calculate the sigma. So this is our residual standard error 1.367. Now what we can do, we can create a band 0.96 times sigma, if colored maybe some different color, maybe brown, and we take LTY equal to 2. We have to take brown, yeah. And similarly, this is lower bound. This gives us a lower bound, you can see. And similarly, we can create a upper bound as well. So now you can see there is a upper bound. Okay, and interestingly, looks like within the bound all data points are nicely fitting in. So it's a pretty decent model. Now what we will do, we can just plot this. We can now do the prediction in this fitting is inside the training data. So what we need to do is we need to look into how it is doing in the test data. So do prediction in test data. So what we will do, data test $red equal to predict mod 1 new data equal to data test. Now if you go to the test data set, we got all the predicted values. And now similarly we can do the plotting of first the test data set, and we have only 5 years of data as test data set. We don't need to keep it. And so this is our test data set. Let us zoom it. This is our original test data set, and now we can draw the lines here. So this will be just, we have to follow it in this way, and instead of fitted values we have is thread. We don't need to clip it. So looks like it has done okay. But we should do a prediction band, and let's see if it is inside the prediction band or not. So we have to just take this, minus 1.96 times sigma. We would like to use some different color, maybe blue, with LTY equal to 2. So this is our lower band. And we have to do an upper band as well. So all I have to do is here, we made it plus, and let's draw the line. So in the test data set, most of our predictions are within the 95% predictive interval. So we can say that this is a simple model with some sine cosine feature, and then it has done pretty good. Now, little bit interesting point I would like to make here. So if you see our data set, right, our data set is in 2 dimension. Effectively, from a train point of view, we have effectively time and the average time, the dates and the average temperature. So we have only 2 variables, average temperature and the time. From there we have created these These two variables, sine and cosine, are our engineered feature. Okay, these are our engineered feature. Sine omega t and cos omega t are engineered feature. So with the engineered feature, we fit a nice model and which is doing pretty reasonable in terms of predicting the temperature. So we will stop here, and we will continue on it. You can always ask me one question, that why we are stopping at only 2 sine cosine Fourier feature. We can always go for higher order Fourier feature like sine 2 omega t cos 2 omega t sine 3 omega t cos 3 omega t. In the next lectures, we will do those hands-on with the higher dimension. But remember that more feature we will put, it will add more complexity in our model. Our model will become more high dimensional. So this has some advantage and disadvantage. We will talk about those increasing model complexity in the next lecture. Thank you very much. See you in the next lecture.